Alright, 7.2 is very similar to 7.1. Instead of exponential growth, now we're dealing with exponential decay. So some examples of things that decay exponentially, we have a cost of living, depreciation of a new car. That might be a little more familiar with what we've heard about, how your car might decrease in value a fixed percentage every year. Let me show you some quick examples with just a comparison. If you were to start with a number like 32 and subtract 2, you would get 30, and subtract 2 again, you'd get 28, subtract 2, we'd get 26. So we are decreasing by a fixed amount. This is not what exponential decay looks like. For exponential decay, you will decrease by, exponentially. Your numbers are going to get smaller in a hurry. So if we look at that same example of 32, this time think about multiplying it by a half. Now if you multiply it by a half, that's the same thing as dividing it by 2, and we get 16. Divide that by a half, and we get 8. Divided by a half, multiply by a half, you get 4. Times a half, and you get 2. So you can see our numbers are getting smaller in a hurry versus just, what we had going up here. So this is the idea of exponential decay. Your decay functions are, exponential function, it looks the same, still that y equals a times b raised to the x power. Only this time what's going to make it a decay function rather than a growth function, it's all about that b value. If your b value is between 0 and 1, then your function will be a decay. Remember, for your growth function, the b value was greater than 1, and that meant our functions were growing. If it's between 0 and 1, then your functions are decaying. The a value, again, for it to be an exponential growth or decay, that will still be greater than 0. So if we take a look at our graph, it looks very similar to what you guys saw in 7.1. In 7.1, the graph went more like this, and it was growing exponentially from left to right. This time it will be decaying from left to right. And you can see the graph starts here and it just goes down. And these graphs also will have that asymptote, again, that line that your graph will approach but will never cross. So here's where the asymptote is. And it's going to be this horizontal line at y equals 0. Now, in 7.1, you saw your graph shift up and down. That will change where your asymptote is. That's going to line up with any vertical shift you have on your graph, but just keep in mind that your exponential decay functions have an asymptote as well. Right here, just a few quick examples to think about whether or not what we're looking at is growth or decay. So what you want to do is take a look at that b value, whatever the exponent of x, whatever the base is for that exponent. This b value is a 5, and that is not between 0 and 1, so that would be, or that's bigger than 1, that would be growth. Here, our b value is a 1/4, which is between 0 and 1, so that would be an example of decay. Here the b value is 0.4, between 0 and 1, decay. Here the b value is 2.5, because that's bigger than 1, that's going to be growth. So you guys will graph these functions. What you're going to be doing is graphing the function without any shifting. So in this case, y equals a negative 1/2 raised to the x power. But I just want to point out your decay functions also have shifting. So just take a look for whatever's up there with the x is shifting your x's. It's tricky though, so shift in the opposite direction. So you would go to the right 2, and then anything off in the end is your vertical shift. So you would go down 1 on this graph. Again, you'll see a video on that, but just a heads up that similar graphing from 7.1. We also have exponential decay models. This is when a real-life quantity decreases by a fixed percent each year. We saw exponential growth models where it was increasing by a fixed percent each year. It looks pretty much the same. The only difference we're going to see is in the equation y equals a times, before what you saw was a 1 plus r, this is a 1 minus r raised to the t power. A is still the initial amount, and r is still the percent decrease written as a decimal. But again, this will be tied to those word problems where something is decreasing by a fixed percent each year.